Our last video of the unit is going to be about Newton's third law of motion, and that's commonly called the law of action and reaction. When you're done watching this video, I want you to be able to say, I can state Newton's third law of motion, identify a pair of interaction forces, and explain why the accelerations caused by an action force and a reaction force don't have to be equal. So the forces will always be equal, but the acceleration will not. We'll explain more in a minute. Newton's third law of motion is a pretty famous one, and you've probably heard this before. So simply stated, you could say, for every action, there's an equal and opposite reaction. So in this example, there's a man pushing on the wall, but Newton says that forces exist in pairs. So not only is the man pushing on the wall, but the wall is pushing on the man. Here's the action, and here's the reaction. Now we've seen this before. What Newton said was forces exist in pairs. Now when we talked about forces and vectors, we used examples like this, where there's a box sitting on a table. And we said there was a force of gravity, the earth pulling on the box, and then we said that there was a pushing force of the table on the box, and we called that normal. So just like these forces exist in pairs, Newton says every force exists in pairs. And he came up with a term for that, and that's interaction. So an action-reaction pair is called an interaction. That's an important term. How you can differentiate or tell the difference between an action force and a reaction force. So the action force is going to be the initial force, and the reaction force is going to be the force caused by that action force. Here's an example. So there's a person that's swimming, and how you swim is to push against the water. So in this picture, the swimmer is pushing against the water, and the water is pushing against the swimmer. The swimmer initiated the force, so that's going to be the action force. The water pushing against the swimmer is the reaction force. Your book has like a really good formula to help you identify an interaction or an action and reaction pair. First, what you should do is figure out what two objects are interacting, and we're going to call those objects A and objects B. Then what you would say, if there's an action that's object A on object B, then the reaction, there's a typo there, is going to be B on A. So what are the two interacting forces here? The swimmer and the water. So the action is the swimmer is pushing on the water, so the reaction is the water is pushing on the swimmer. One thing that you have to keep in mind is that the action and the reaction forces can't be acting on the same object. So in the case of the swimmer, the action force is acting on the water, and the reaction force is acting on the swimmer. Let's look at another example using our formula. Here's a hammer and a nail. Those are our two interacting objects. What's the action force? The hammer hits the nail. What's the reaction force? The nail hits the hammer. Here's another example with the car. What's interacting? The car is interacting with the road. So the action force is the car pushing against the road, and the reaction force is the road pushing against the car. You getting the hang of it? Now where it can become kind of tricky, I think, is when you're dealing with things like the Earth. So here's an example. Here's our friend, this famous Galileo experiment. And you remember when we watched in class the recreation of that Galileo experiment where they dropped a whole bunch of stuff from the crane? Well, Galileo famously dropped a cannonball from the Leaning Tower of Pisa, and he dropped cannonballs made of two different things. So that's why this example is used. So in this case, what are the two interacting objects? Well, you've got the cannonball, and what's exerting a force on the cannonball? Well, that's going to be the Earth. So in this case, A is the cannonball, and B is the Earth. Now what's really obvious here is that the Earth is exerting a force on the cannonball, but according to Newton's third law, the cannonball actually exhibits a force on the Earth. So how you would say this interaction is the Earth pulls on the cannonball, and the cannonball pulls on the Earth. Well, why can't you see the cannonball pulling on the Earth? We'll talk about that in just a minute. Especially when you're given examples of like a cannonball pulling on Earth, sometimes it's hard to believe Newton's third law. So there are a lot of cool examples where proof is shown of Newton's third law in action. So here's a case where a girl is shooting a basketball. Now what normally happens when you shoot a basketball is the force or interaction between your shoes and the floor keeps you in place. And that's a friction force that's involved. So if we take that same scenario, but instead put the girl in roller skates, we can see evidence of the ball pushing on the girl. So the girl shoots the ball and pushes the ball away, and evidence of the ball pushing the girl would be the girl would move backwards if she was on roller skates, because there'd be no friction between her and the floor. Another example, our first example that we looked at was a guy pushing on the wall. And we said the wall would push on the guy. Well, in this case, here's a woman that's on a skateboard. And when she pushes against the wall, you'd see evidence of the wall pushing against her because she would move on the skateboard. Another classic example involves a boat. And if the person is pushing off of the boat to jump onto this dock, you'd see the person moving forward and the boat moving backward as an interaction, an action-reaction pair. Another classic example of an interaction is between a cannonball and a cannon. So when a cannonball fires, that cannonball shoots out really fast, and there's an equal and opposite reaction on the cannon, and that's called recoil. Now this cannonball is moving super fast, but the recoil of the cannon isn't super fast in the opposite direction. So, the question arises, if these forces of action and reaction are equal, how come the velocities aren't equal? And when we address this question with the cannon and the cannonball, we're also going to be addressing this question with Galileo dropping a cannonball towards the Earth. And this cannonball is accelerating towards the Earth, and the Earth accelerates towards the cannonball, but you can't see that. The underlying reason why the velocities aren't equal of the cannonball and the cannon, or in this case the cannonball and the Earth, is grounded in Newton's second law. Acceleration equals force over mass. Now in Newton's second law, mass and acceleration are inversely proportional. So, when mass goes up, acceleration goes down, if the force is unchanged. So, in the case of the cannon and the cannonball, if it's the same amount of force going both ways, this force is moving a low mass cannonball, and that means the acceleration is going to be very high. Comparatively, the mass of the cannon is very high, so the acceleration of the cannon is going to be very low. If we look at this in the case of the cannonball and the Earth with Galileo's experiment, the cannonball has a really, really low mass compared to the Earth, and so its acceleration is going to be very, very high. The Earth has a mass that's really, really high compared to the cannonball, so its acceleration is going to be very low, to the point to where you can't even see it or notice it. So remember, action and reaction forces make up something called an interaction. and this is the basis of Newton's third law, that for every action there's an equal and opposite reaction. Those forces, the key is equal and opposite, so you should be able to identify an interaction and be able to explain something like this and state Newton's third law.